We could see it, but I don't think anybody else could see it. So, all right, now we're shared, and then I'll stop sharing when we go to Jeff. So this is a little bit about our architecture. You've heard a little bit about the fact that we have a shop floor viewer web browser, as you can see in the top left. That is a thin client browser. So essentially what happens is when you engineer your process, you publish. When you publish to the shop floor viewer server, which is a whole separate server that could be cloud-based, and you could do on-prem for your authoring of your process. You could publish to a cloud server. It doesn't have to be a cloud server, but the bottom line is it is a server, IIS server, that all of the client shop floor viewer interaction is in a thin client environment, which means you're on a web browser. So our entire shop floor MES system is a web-based tool. Okay? Thin client web-based tool. Not true for our authoring environment, but definitely true for our shop floor viewer environment. And so the web browser is essentially what you see. We test on obviously Chrome for, we have some Intel Nooks you'll see here in a moment, those little small Intel PCs, but we also test on Raspberry Pis in the Raspbian environment with the Chrome browser on that. They work great. So those are our web browsers. Now also we have another server that's running Factboard, which is our Andon system. Okay, so and the Andon system, Factboard, is essentially a system that reports the status of the shop floor like any Andon system would. It receives transactions from shop floor viewer, just like it would receive transactions from any device in the world. In other words, our Factboard Andon system completely receives what are called JSON transactions. These are essentially little text snippets of information. So there's nothing special about shop floor viewer telling our Andon system something happened. You could have your Excel spreadsheet in your office tell Factboard something happened. You could program your CNC machine tool, tell something happened. You could have something in your car blow up and tell Factboard something happened, right? Factboard doesn't care where it gets the information. It gets it wherever you want it to get it from. So Factboard is a separate system, but of course, it's used a lot with our shop floor viewer because when things happen on the shop floor viewer MES side, we want to tell Factboard so the world gets to know about it. But it also is a thin client web-based system. And of course, then, as you'll see later, our PFET application, which is our handheld Android scanner type apps, tablets, apps, and things like that, which are used for shop floor. They also have a system that is client-facing. We also have something called the ProPlanner IoT service. Now, you'll notice there's some little dashed lines around there. The ProPlanner IoT service is an actual software program that runs on your subnet in your factory. That's only needed when you're talking to shop floor automation on that subnet in that factory, okay? So it is a piece of software that runs on a computer somewhere on the network where the industrial automation that we are talking to works. So we talk to that app in a secure way. That app can talk to anything on the subnet any way we're allowed to, which the bottom line means 99.99% of the time is in a non-secured way, but that's okay. It's up to you how you want that to happen. But that is another tool that we have that's installed architecturally. Of course, what is it we're talking to? Well, it could be PLCs, it could be light towers, and on light towers, it could be DC torque tools, it could be whatever. And we have a whole bunch of stuff here. We're showing you how that works. So that's what's going on. You can see on the bottom, the data center. So those are actually the servers that are talking to the apps on the top left, which are web-based apps, and our IoT service in the top right, okay? So the hard work is done in the bottom left by the server technology that's on your, let's say, you're in your network or on Azure. The top left is what you see, and the factory network on the top right. So that's essentially the control system, these databases, and we have these secure web service APIs that are talking to shop floor viewer, PFET, and the Internet of Things device. Now, let's talk a little bit about specifically devices. And I'm drilling down, talking about just industrial Internet of Things. So how do we do this? Well, on the left, you have assembly planner. That's process authoring. On the right, of course, shop floor viewer, which is our MES environment for which the DC torque tools are communicating. What I want to say is, the question is, why should ProPlanner be talking to my tools? Right? What's the whole business value proposition of this? Here's the deal. When we're dealing with MES systems in assembly, they're human-centric. This isn't automated testing. This is a human who gets information but also uses tools that are smart. This is a very different MES problem than one we had 10 years ago, the one we had 20 years ago. One of the things we are doing then in ProPlanner is we're saying When this operator torques this bolt, I want it to use this PSET, this program in the DC torque tool. I want to use a PSET 7. But if it's this model with this option, I want to use a PSET 6. Or if it's this model with this option, I want to use this tool, this nut runner, with a PSET 42. Okay? So what we're doing is we're telling the automation, the scanner, the DC torque tool, the PLC, we're in charge of understanding the model option rules. That's part of the process plan. That's part of the bill of process, okay? We know, the bill of process knows what instructions to deliver that operator, the human, for which model and option they're working on at this particular moment in time, right? That's the knowledge in the process that we publish to the shop floor work instruction. All we're doing now is publishing the same information to the tools. So I tell the robot, okay, I want you to do this particular program at this particular moment. Don't care why, we take care of that. We tell the robot to. We don't have to build all the model option configuration rules in the robot's logic, only to then when the process engineer changes them, remember, oh, darn, I have to go back out and reprogram the robot. You don't have to do it. All you got to do is make sure that the DC torque tools have all the different torque profiles that we may ever use in them. We'll decide when we want to use them. We need to tell the scanners and the torque tools or the other tools like the PLC what to do. We decide when to execute it. And more importantly, if I have 4 stations of torque tools all set up in different parts of the plant and I move a task from one station to another, automation engineer doesn't have to do anything. As long as that PSET 12 is in that other torque tool as well, as long as the nut runner that we need is available to that operator, we publish the work instruction and bam, that torque event now happens in station 12 instead of station 6. No automation engineer had to go out and reprogram 6 and reprogram station 12 and test and validate and run. We can literally go from 8 in the morning on one line balance with one set of automation profiles to 10 in the morning with a different set of automation profiles. Now, obviously, if a physical nut runner needs to be moved or something like that, that's going to happen. And we have a report for that. So we generate a report saying, hey, this nut runner needs to be changed. Automation engineer can make that change. But the automation, the software logic, the rules are all automated and simplified. So we, in Assembly Planner, then, our resource library, you've been using resources, you call them tools, is getting smarter. So now a tool also knows that it's an automated tool, which means that the shop floor viewer needs to notify a piece of equipment on the floor. And so we add that logic into the resources. We give it the values, the knowledge, the PSET 7, if it's a DC torque tool or whatever PLC program knowledge it's needed, is added to the attributes, the properties of the resource in Assembly Plan and published to the shop floor viewer. Okay? All the shop floor viewer does is say, oh, do this activity, do this work step. For this model option, I need to send this information to this tool. And that's what it does. And you're going to see us do that here in just a moment. So that's how that works. A little bit on authoring. And so just real quickly, what I have here is a view of the resource. So I have defined a torque tool. I've set up that this torque tool is called a ST1 DC torque 6N. And whenever I drag that into my work step, because work steps talk to tools. So that's the only thing, training class, but an activity needs to have a work step if it's going to talk to a tool. And we drag that intelligent resource from the resource library into that work step. And I've now activated those properties of that tool to that work step. So when the shop floor viewer sees that work step, it knows, oh, send this information to this address, to this tool to make sure that we're communicating correctly. So that's the knowledge you build into the resources. And then this is mapping. So here's where I'm in my activity. Here's my work step. I go into my tooling and I've drug in those properties. Anybody who's ever done test types in work steps, very similar concept. In fact, we're extending the test type concept essentially to do DC torque tool integration. So that's a quick overview of why we're doing this and how we're doing this. Let's see what we're going to do. And so I'm going to turn it over now. I'm going to stop my sharing. We're going to go back and turn the video on. And I'll turn it over to Jeff.
All right. So I've got a mock assembly line here. So it's a 2-station setup. I've got shop floor viewer on 2 screens. So we're treating this as station 1, and then station 2, and then I've got backboard Andon up on the top. To take you through some of the devices we've got, like Dave mentioned, we've got Intel NUCs, so just small PCs running shop floor viewer, and fact board. I've got 2 of those. COM port, just serial scanner, a Zebra scanner, hooked up to the COM port of the first station. I've got a wireless Bluetooth tool connected to an Atlas Copco PF6000 and a wired torque tool connected to the PF4000. And then I've also got an Allen Bradley Micro 800 series PLC connected to a couple buttons and switches, and an Ethernet light tower as well on the top. So that is our Andon signal for this assembly line. A couple things you can't see we've got going on. As Dave mentioned, the IoT service running in the background on a PC connected to the same subnet as all of this fun stuff. And then as well, we've got a KEP server, OPC UA server. It doesn't have to be KEP server. They just offer a couple drivers that you can use to bring all your protocols into one place. So we're talking to the Atlas Copco tools with an Atlas Copco open protocol. It doesn't only work with Atlas Copco. It's a universal torque tool communication protocol. And then the PLC connected devices are all OPC UA for this demonstration. So what I'm going to do is I'm going to take the barcode scanner and sign on to my first unit. So station 1 will take me to the process tree just because of my role privileges here. I'm going to go and sign on to that. And as I sign on, you can see a couple things happened here on the screen. Oh, sorry.
Go ahead.
Good. All right.
Oh, hang on just a second. We're losing our connection. Why would we do that? We're not sharing the screen. There we go. Just keep an eye on.
Okay. So to take it back a little bit, I'm not sure when it cut off. Scanned a barcode, took me to the process tree. I signed on to my first activity at this station, which every work step in this activity has a device. So the first thing that it did was call this first activity or first work step here, which is using my wireless torque tool, which has got 1 cycle. So I've got 2 different work steps right in a row, which are going to call the torque tool. And that is because as you'll notice as I index through these torques, it'll index my images as well. So you can kind of see on the screen, I've got 2 bolts here, and then 1 is highlighted yellow, indicating that's my first torque. So I'm going to go ahead and do that. The tool tray is also on the right side here, which is tied into the first torque tool. So I need to choose the right socket here. And I'm running down the first bolt. I get a pass, moves right to the next work step, and reflects on my work instructions as well. So kind of hard to see, but what it displays when that happens is the result torque and just a green indication that it's good. So what I'm going to do now is fail a torque, and I get red on my controller, red on the work step with a quick summary as to what happened. So it says torque result low, angle result okay. And it saves that data with this work step. So once I go and pass a torque, it's not going to lose that data. So you know when you're looking back at your data, you've got, okay, I failed the torque 3 times. That's what it took to get there. So also in the resource library, you can configure a certain amount of retries to do for these work steps. So this tool, I'm allowing 2 retries. You can allow infinite retries. You can allow however many you want. What that does is once I fail a second torque, it fails everything on the screen, gives the same indication. Track board will show red now as I've created a hot issue. And then my light tower also reflects the status of the station. So now the tool's locked out. I can't do anything. with the right privileges, you can go back. I'm going to reset this hot issue. Close out my issue, and I'm going to just restart the torque process. Everything returns back to a normal state. My Andon's green, backboard's green. I can go ahead and torque my second bolt. So that one finishes, moves on, and now I'm calling my first PLC device, which is kind of a mock tool tray. I have a couple switches here and lights associated with them showing me which switches to flip. So it's easy to visualize sending a job from Assembly Planner. What I'm doing to configure this is essentially the same thing. I'm sending it a number which corresponds to which lights and switches I want flipped for this particular unit. So there's no custom hard-coded values when I call this. The only thing that's hard-coded from the PLC side is which inputs am I using, which outputs am I using, because these are all wired directly to the I/O of the PLC. So I'm going to go ahead and flip these switches. That completes that activity. I get to my second activity, which is just telling me to back out these bolts and use a button on the PLC to confirm that I did that. So I'm going to back out bolts. And then go ahead and hit my confirm. And then since this is the last activity in this operation, I have an auto sign off here. You can't really see from the screen, but there's a timer saying I've got this much time before I'm going to auto sign off and complete that activity. So it returns me back to the process tree in this instance, and I'm ready to sign on my second station. So I'm going to sign on to the same serial number, second station, which is just a single activity, torque activity as well. But this time I'm using this torque tool, so the PF4000 wired tool, and I'm going to just, something to note here too, this one is a batch process, so a little difficult to see, but instead of one box, I've got two boxes showing how many torques I need to complete. So we can call either individual P sets, so if you just want to call the P set, or also the job. So a job could be a collection of 5 P sets and a whole bunch of different numbers of those to complete. So we've got, we're just calling a full batch process here. Maybe you don't want to control the work instructions to index every time you complete a torque. So it's populated all of that, and it's going to get 2 torques, and then move on to the next one. I'm using the same operator confirm. It's a shared PLC, same device. So I can go ahead and confirm that I've finished that process. Same activity sign off. And I've built a unit. So does anyone have any questions from there? And I guess for those of you in the room, this is the, I've got a whole bunch of units set up to run through this exact process. I get some hands-on feel for how that works.
Any questions on people from the room, and then we'll open it up to the people online to see if there's any questions. Go ahead, Dave.
Timestamp. Don't worry. You get a timestamp.
So we use the term interlock. So if you think about the fact that I could have a work instruction that has 8 activities, none of those activities ask the user a question. None of those activities require the user to certify they did something. None of those activities use a tool. The reality is I'm going to get a time when I start the 8 activities and when I end the 8 activities, right? But if I ask a question somewhere in there, if I require them to hit a button, if I require them to respond to a tool, that's a timestamp that's recorded to the unit. So now I have an interlock, right? So I have a time element. So to the folks from McNeilis, one advantage of asking the user to hit a button that I did this is, first of all, make sure they read the instruction, but also I know when they did it versus, or these interlocks, requiring them to interact with the PLC. So anytime a piece of equipment in the station does something, we document it. So in a way, if you want to collect accurate data about your process, you could have either automated or manual interactions with the system so that you have points where time is collected. Otherwise, we just don't know, right? I mean, anything can happen. So did that help answer the question? Yeah. So the more you do, the better. And so some of these things, but the other thing is, and I think that somebody, I can't remember who mentioned it. On the other hand, other organizations don't want interaction, right? They want the operator to start a job and do the job. They don't want them hitting screens and interacting with tablets. And, so in a way, that's why we have auto sign on, auto sign off. That's a polling scanner. So we could have it always reading. And if I wanted to record the serial number of a part I put on, I could just move the parts under the barcode scanner, just so it beeps at me that it recorded that serial number, and then I could put it on the product, but I don't have to touch the scanner. I don't have to hit a button, right? So we do spend a lot of time trying to remove touches to keep stuff as hand-free as possible. But still, since the device read a barcode of that unit at that time, I still have a timestamp, even though the human didn't do anything special outside of just make sure that when they were picking up the motor or the transmission and moved it under the scanner to get that recorded. Did we have any questions online? If someone does have a question online, feel free to unmute yourself. Oh, sorry, we do have a question here. Go ahead.
So we're dealing with torque, right? What about a laser scanner that measures distance? So if I've got quality distance.
Yes.
I don't want to do that manually with a calculator.
No, you could, but that would be a great case where if, let's say I had a distance measuring device that was hooked up to a USB port or an Ethernet port, if the operator hit a button when it is they wanted to measure the distance, we would measure the distance, we would record it as we do a test type into the unit, and we also create a timestamp activity so I know the time before we asked that distance and the time from that distance, right? So that, yeah, that works fine. That's something that we could do, very easily. So there are really kind of two classes of inputs. One is, we'll call it keyboard USB port. These would be local device based, so you could hook that distance measuring up just to a USB port. But of course, then only that tablet, only that NUC, only that station can do it. The other one would be where it's on the subnet, Ethernet, and then we grab the device. We for example, this Andon light tower that we have up here, that is actually an Ethernet tower. So that's hooked up to the subnet Ethernet. I could have that tower in a whole different room and still activate that green light when this happens. But we could have just as easily bought your more normal 24 volt, light tower with manual lights and wired it up to either the PLC or to the, by the way, the PF6000 also has a Modbus communication capability. I could have hooked it up to the Modbus there and programmed to OPC Classic to turn that on, right? So a lot of options exist.
Yeah, the same thing with the distance, like with the OPC and PLC integration. You can pretty much do anything, hook up distance, analog distance measurement up to there, and also have it confirm with that so that it's in range. And you can run a job or set your max min through process authoring as well. So you don't need to have specific min maxes stored in your PLC or in the device even. You could, or you could set it there and have it written to OPC tags and have that read as the device is running.
Do we have any questions online? For the folks online, if you want, you can unmute yourself and ask a question.